On a warm July night in 1981, the lobby of the Hyatt Regency Hotel in Kansas City was filled with music. It was the Friday Tea Dance, a weekly event that drew crowds from across the city. A live band played on the lobby floor, and 3 floating walkways stretched above the crowd, suspended from the ceiling by thin steel rods. People crowded these walkways, leaning on the railings and looking down at the dancers. Then, at 7:05 p.m., a sound cut through the music. A sharp, metallic snap. And then, the walkway that spanned across the 4th floor of the atrium collapsed. It crashed into the 2nd-story walkway directly below, and 40 tons of concrete and steel fell into the lobby. 114 people were killed, more than 200 were injured. This was the worst structural disaster in American history at the time. But how did this happen? How does a brand new building, designed, inspected, and certified, fail so catastrophically? The hotel had opened less than a year earlier, which is what made this disaster so unsettling. But the investigation that followed revealed a fatal flaw. What they found wasn't only a technical mistake, but a shocking oversight that should have been caught long before the walkways were ever built. In this video, we'll look closely at the investigation that exposed this fatal flaw, why the collapse was unavoidable, and the reforms that followed. When plans for the Hyatt Regency Kansas City were first announced in the mid-1970s, the city was in the middle of a transformation. After years of urban decline, Kansas City wanted a landmark, a structure that could symbolize renewal. That vision came from the Crown Center Redevelopment Corporation, a subsidiary of Hallmark Cards, and led by its founder, J.C. Hall. Hall wasn't an architect or engineer, but he understood atmosphere. He believed that the way a space feels can define how people remember it. When Hall visited the Hyatt Regency Atlanta, he stepped into its vast atrium, stopped, and said aloud, "Jesus Christ." That instant of awe, that involuntary reaction that he had, became the design goal for Kansas City. Inside Hallmark, it was called the JC moment, a space so striking that visitors would instinctively pause, look up, and feel a sense of awe inside something extraordinary. The architects working on the design for the new hotel centered their entire concept around that moment, and their design philosophy was summed up in 3 words: light, height, and life. The atrium would be the heart of the hotel, 5 stories tall, enclosed by glass, open and bright, and alive with the constant movement of guests. They studied what made the Atlanta atrium unforgettable. It was both the scale and how people were woven into the space with interior balconies and elevators that rose up through the center of the atrium. To recreate that in Kansas City, they needed more than just a tall open space, which would be a copy of what worked in Atlanta. They needed something new. The solution was a series of 3 suspended walkways, crossing the atrium at the 2nd, 3rd, and 4th floors. These floating bridges were designed both as functional walkways and as visual anchors, bold lines suspended in the air. Guests could stand above the lobby, lean on the railings, and watch the crowd below. Structurally, the concept was designed to be very elegant. Each walkway would be supported only by a few slender steel hanger rods connected to the roof. Each level would carry only its own weight and be structurally isolated from the others. On paper, this worked beautifully. But translating this elegant design to the real world introduced complications that we'll get into later. When the hotel opened on July 1st, 1980, the vision had been realized, almost exactly as Hall imagined it. The atrium was filled with natural light, and the suspended walkways seemed to float above the lobby. Guests describe walking in and immediately looking up. The architects had captured the JC moment. The Hyatt became an instant landmark in the city. In the year that followed, tea dances, receptions, and weddings all took place beneath these floating bridges. But even in the first year, there were warning signs that the structure was failing. Just after opening, construction workers noticed that the skywalks appeared to be sagging by almost an inch. The handrails were not aligned. There was a deflection in the floor, and the beam that held the walkway to the ceiling rods seemed to be bending. However, these alarms were never reported. only left as notes and maintenance logs. But these signs should not have been ignored. They were the early structural warnings that something was seriously wrong with the design. These notes should have been investigated immediately, but no one did. So what did those early warning signs mean? And why, in a building so carefully designed, did no one stop to investigate? The Hyatt's walkways were designed to be grand structural statements. The atrium design featured 3 suspended pedestrian bridges on the 2nd, 3rd, and 4th floors, crossing the open glass and steel lobby. The engineering firm GCE International Inc., under principal engineer Jack Gillum and project engineer Daniel Duncan, produced drawings showing continuous hanger rods supporting the walkways. Each rod extended from the roof trusses through the 4th floor walkway box beam and then through the 2nd floor walkway and ended below this 2nd floor. The concept was to transfer each walkway's load directly upward through a single rod path, thereby isolating the loads of each bridge. In this configuration, every hanger rod supported only the load of the walkway it passed through, and the stresses were distributed evenly between the connections at each end of the box beam. The hanger rods were secured to box beams that were fabricated from 2 standard C-channels welded together to create a hollow rectangular section about 8 inches wide. The rods passed through holes in the top of these box beams and were anchored by washers and nuts. The steel thickness at these bearing points was only 0.179 inches, while the washers that distributed the load had a bearing area of about 7 square inches. Under the original calculations, that produced a bearing stress of approximately 1.9 tons per square inch, which is already approaching the yield strength of the material. According to the National Bureau of Standards, the original design's connection capacity achieved only about 60% of the minimum strength required by the Kansas City Building Code. So, even if the structure had been built exactly as it was drawn, it would not have met the local safety requirements. Also, the design had little redundancy. There was no secondary support system if a connection were to fail. So, because the walkways were fully suspended, the entire load path depended on the integrity of a few square inches of steel at each connection. On paper, the design was just workable. The distributed load of the walkways and the moderate occupancy anticipated for the tea dances fell within expected ranges. Even if not fully meeting safety codes, there was still a little room for slightly higher than expected loads. And so, with tight deadlines closing in, the design was approved and the project moved forward. But the original configuration assumed perfect fabrication and precise alignment of all elements. Even minor imperfections like slightly oversized holes or imperfect box beam welds could shift stresses and concentrate them along the thin edge of the box beam. That would cause the washer to put pressure on the beam wall, creating local yielding. The NBS and the ASE later noted that the original design had almost no reserve strength to absorb that kind of imperfection. By early 1979, construction was running on a tight schedule. The project had faced delays in foundation work, and Hallmark wanted to open the hotel by mid-1980. When Haven Steel Company, the fabricator responsible for the walkway assemblies, received the engineering drawings, their field teams immediately flagged a practical issue. Threading and installing a single 40-foot-long continuous rod through multiple floors would be extremely difficult, especially to meet the precise needs of the building safety. To fit the rods, the walkway slabs and box beams would have to be perfectly aligned, and the threads on each end could easily be damaged during assembly. Building such a system in a busy atrium structure added risk and time. So, Haven Steel proposed an alternative. Instead of one continuous rod that would need to be run through both walkways, they would use 2 shorter sets of rods, one suspending the 4th floor walkway from the ceiling, and a second suspending the 2nd floor walkway from the 4th. It was presented as a fabrication convenience, not as a fundamental structural redesign, which would require load recalculations. So construction went ahead. In February 1979, Haven submitted the revised shop drawings to GCE for review. The engineers approved them without recalculating the load path, stamping them with the seal of approved for fabrication. And so construction continued. At the time, such small adjustments were considered routine. The logic was that the change didn't alter the overall geometry, only the installation method. But what actually changed was fundamental. the entire load path of the walkway system was altered when the design was changed from one continuous to two separate hanger rods. Unfortunately, that critical distinction would not be realized until a year later when investigators compared the original drawings to the structure that fell. Before we get into the full investigation, if you want more engineering deep dives like this, don't forget to subscribe, and if you're enjoying this video, give it a like. I really appreciate your support. At 7:05 p.m., the atrium floor of the Hyatt Regency was crowded. The live band was in full swing, and guests filled the walkways, watching the dance below. Then came the sound, a deep metallic crack. Sally Firestone, who was 34 in 1981, said that's all she remembers. She was perched on the edge of one of the skywalks when the fourth floor walkway dropped. She remembers later waking up in the hospital, shocked to hear the news, but unable to remember what exactly happened. The 64,000 pounds of steel and concrete fell onto the second floor bridge below, and together they plunged more than 30 feet into the lobby. The collapse lasted less than 4 seconds. The aftermath lasted through the night. Rescue calls flooded the Kansas City Fire Department within minutes, and first responders were on the scene by 7:15. Dr. Joe Wakerl, former Kansas City medical director, was one of the first on the scene. He couldn't have anticipated what awaited him at the scene, saying, "I walked in, and there were electrical wires swinging and arcing. There was water running out of the pipes, which had been severed by the skywalk collapses. I was walking in 6 to 12 inches of water. Everybody was sort of in chaos and screaming, and people were attending the best they could to injured people and relatives." He set up an improvised triage line, and firefighters used power saws to free survivors pinned beneath the concrete slabs. Over the course of the 14-hour rescue operation, the rescue workers pulled 29 people out of the debris alive. By 10 p.m., the Hyatt's lobby had been transformed into an operating room. Guests who'd escaped injury carried stretchers made from tablecloths. A nearby radio station broadcast urgent appeals for blood donors. Hospital corridors across Kansas City filled within the hours. Reporters gathered outside as the magnitude became clear. The twin skywalks had fallen directly onto the densest part of the crowd. Most of the victims were on or beneath the second floor bridge, dancers, hotel staff, and bystanders who never had the time to move. Rescue crews worked through the night, and shortly after dawn, the last trapped victims were reached. In all, 114 people were dead, and 216 were injured. At the time, this was the deadliest accidental structural failure in American history. Among the victims of the collapse were teachers and military veterans. The Kansas City Star reported that the youngest victim was only 11 years old. The atrium, once the heart of Kansas City's renewal, was now a field of questions. What had given way? Was it a construction or design error? And how could a structure less than a year old and inspected and certified fail so completely in the span of 4 seconds? And what investigators uncovered would change the field of structural engineering forever. In the hours after the collapse, the Hyatt atrium was unrecognizable. Rescuers moved through the clouds of dust, stepping over broken glass and twisted metal. What remained was an immense field of debris, the 2 collapsed walkways broken on the atrium floor. And as the rescue lights dimmed, a new team arrived: engineers, inspectors, and investigators. Their task was to understand exactly how and why the walkways had failed. There were several theories that emerged as the engineers started to sift through the wreckage. Some suspected that the hanger rods had snapped, perhaps a brittle steel failure under the sudden load of the partygoers. Others pointed to the roof trusses, theorizing that the ceiling connection had given way, sending the entire suspension system down with it. But when the debris was mapped, investigators noted something interesting. The walkway slabs themselves were largely intact. The failure hadn't occurred in the middle of the spans, where one might expect bending failure under overload, but at the junction points, where the hanger rods attached to the box beams. Within days, engineers from the National Bureau of Standards, the Kansas City Building Inspection Department, and independent consultants hired by the Kansas City Star began combing through the wreckage. Their task was to reconstruct the final moments before the collapse. The physical evidence they found quickly began to rule out some of these early theories. The The roof trusses were intact, and the hanger rods had not snapped. In fact, many of the rods still hung from the ceiling, unbent, and, critically, with their nuts and washers still in place. That meant that the failure hadn't started at the roof connections, but more likely at the walkway box beam connections. Investigators carefully examined the remains of the fourth floor box beams, where the upper hanger rods had connected. Each box beam had been punched through from below. The washers and nuts that had once held up the walkways had torn directly through the thin steel walls of the beam. The forensic team also realized that this was not a single fracture event, but a progressive overload. When the first washer punched through its beam, the remaining rods suddenly had to carry an additional share of the load. And with no room for additional weight in the original design, this led to failure of all the beams. Within a fraction of a second, the remaining bolts tore through the beams, each failure increasing the stress on the next until both walkways fell in unison. But this shouldn't have happened with the original design. Within a week of the disaster, the National Bureau of Standards took charge of this technical investigation. The team began by documenting the scene in extraordinary detail. Every section of the collapsed walkways was photographed, tagged, and cataloged before removal. They mapped the precise positions of beams, hangers, and debris fragments, treating the atrium like a forensic laboratory to work out the cause of the disaster. The NBS team's goal was to reconstruct the sequence of failure. To do that, they needed to answer 3 questions. 1. Where did the failure start? 2. What failed first? And 3. Could the design, as drawn, ever have supported the loads that night? Tensile testing of recovered beam samples proved that the steel met ASTM A36 specifications, with a measured yield strength between 36 and 40,000 psi, exactly what it should have been, so it wasn't a failure of the steel beams under the load. Also, the crowd weight alone was not excessive according to the original design. Even fully packed, the load that night was well within the 100 pounds per square foot live load limit that was required by Kansas City code. So if it wasn't the overload of the tea-dance party that night, what caused the failure? The key evidence came from those fourth floor connections. Each recovered section of the fourth floor box beam showed the same distinctive damage. A roughly 3-inch hole torn clean through the lower weld, the edges bent inwards in the direction of the pull. The nuts and washers were still on the hanger rods, undamaged, exactly where they had been before the collapse. It was the beam that had failed, not the hardware. The concentrated force of each washer had pressed into the less than 0.2 inch thick steel wall until it tore through the welded box beam completely. Critically, that weld that ran along the box beams created a source of weakness that eventually caused the failure. Investigators also found subtle signs of pre-failure deformation. Indentations in the steel around the washers, suggesting that the connections had been deforming slowly for weeks, even months, before the final collapse. To confirm their findings, the NBS built a full-scale replica of the connection. They used identical box beams, washers, and hanger rods, and slowly applied load using hydraulic jacks while monitoring strain and deflection. At 20,000 pounds, the first signs of distress appeared, a slight bulge forming under the washer. At 25,000 pounds, visible yielding and a concave depression formed, and at 31,000 pounds, about 15.5 tons, the washer punched through the steel in less than a tenth of a second, duplicating the real-world failure perfectly. The test confirmed that the as-built connection could sustain barely half the load it was designed to carry. Even the dead load, which is the weight of just the walkways themselves, brought the connection dangerously close to failure. By the end of the investigation, the NBS reached 9 key conclusions. Collapse of the walkways occurred under the action of loads that were substantially less than the design loads specified by the Kansas City Building Code. The ultimate capacity of the box beam hanger rod connections can be predicted on the basis of laboratory test results. Under the action of the loads estimated to have been present on the walkways at the time of the collapse, all fourth floor box beam hanger rod connections were candidates for initiation of walkway collapse. Observed distortions of structural components strongly suggested that the failure of the walkway system initiated in the box beam hanger rod connection was at the east end of the middle box beam in the fourth floor walkway. As constructed, the box beam hanger rod connections, the fourth floor to ceiling hanger rods, and the third floor walkway hanger rods did not satisfy the design provisions of the Kansas City Building Code. The change in hanger rod arrangement from a continuous rod to interrupted rods essentially doubled the load to be transferred by the fourth floor box beam hanger rod connections. The box beam hanger rod connections would not have satisfied the Kansas City Building Code under the original hanger rod detail. Under the original hanger rod arrangements, the continuous rod, the box beam hanger rod connections, as shown on the contract drawings, would have had the capacity to resist the loads estimated to have been acting at the time of collapse. Neither the quality of workmanship nor the materials used in the walkway system played a significant role in initiating the collapse. The investigation had revealed the what, but not yet the why. Why was the connection so weak in the first place? Investigators had quickly identified the primary connection points where the failure had originated. At these points, the washers had punched clean through the walls of the box beams, a sign not of sudden shock, but of prolonged overstress. And, as they reviewed the construction files and shop drawings, they put together the puzzle of why this failure had occurred. The hanger rod assembly built on site did not match the original engineering drawings. That small change in design that the construction company made to make fabrication easier led to this extreme failure. Instead of the single continuous threaded rod running from the ceiling through both walkways, the actual structure that was built used two separate rods. One rod suspended the fourth floor walkway from the roof, a second rod was attached below it, holding up the second floor walkway from the fourth floor structure itself. This meant the entire weight of the lower walkway was transferred to the fourth floor walkway's connections rather than the roof joints. The critical load-bearing connection had been effectively redesigned during construction without a single engineering calculation or formal review. One question later, Gillum, principal engineer at GCE, admitted that his office had approved the revised shop drawings without recalculating the connection capacity. The fabrication change had been considered minor, something practical, not structural, that could have been caught with a quick calculation. The NBS would spend months meticulously testing the recovered components in the lab, but even in the first week, the shape of the story had emerged. It was a preventable engineering error that slipped through unchallenged. The sequence of events that unfolded in the Hyatt atrium matched the reconstruction put together by the NBS in their thorough investigation. Here's what happened. First was the washer punch-through. As load accumulated over time, the thin steel wall of the box beam began to deform. Under the doubled stress, the washers slowly pressed into the steel, indenting the edge of the hole where the rod passed through. The steel around this hole began to yield, but this was invisible during normal operation. Next was the initial connection rupture. On the night of the collapse, with roughly 20 to 30 people on the fourth floor walkway and 40 to 50 on the second, one connection reached its ultimate capacity. The washer punched clean through the beam wall, the entire span dropped a few inches. This was the initial crack that the guests heard at the time. Then was a quick load redistribution. The remaining 5 connections suddenly carried the entire load. They were already overstressed, and within 1 to 2 seconds, they failed in rapid succession. Then, it was freefall. The fourth floor span dropped in freefall, striking the second floor walkway below. That second floor walkway was now subjected to the full impact of the upper span, plus its own load, and so its connections failed instantly. Post-collapse calculations show that even without a single person standing on it, the fourth floor connection would have failed eventually under dead load alone. That means the collapse was inevitable from the moment the structure was completed. The crowd that night only accelerated the failure. And so, a deeper question remained. How did a failure this obvious on paper move through every level of review without anyone catching it? When the technical cause of the collapse became clear, attention shifted to the question of who was responsible. The Hyatt Regency walkway collapse triggered a nationwide reckoning with the engineering and construction industries. What investigators uncovered was a paper trail, clearly showing how a single revision slipped through unchecked. And this raised another alarming question. How many other buildings carried similar unseen risks? After the NBS and the ASCE reports were published, the Missouri Board of Architects, Professional Engineers, and Land Surveyors took disciplinary action. Jack Gillam and Daniel Duncan, the lead engineers at GCE International, had their licenses revoked in Missouri. They were also expelled from the American Society of Civil Engineers, the first such expulsions in ASCE's history. And Haven Steel, the fabricator, settled civil suits. But no one faced criminal charges. Gillam would later speak openly about the case, saying in interviews that he stamped the drawings. That means it was his responsibility, and that's what it means to be a professional engineer. Though no one faced prison time, the civil litigation that followed was extensive. In the years that followed, more than 300 civil cases were filed. Victims, survivors, and families sought damages against the hotel owners, architects, engineers, and the fabricators. And after nearly a decade of litigation, the settlements totaled over $140 million. But the real legacy of the Hyatt collapse was in the engineering procedures that changed. Prior to 1981, it was common for engineers to approve shop drawings without performing independent calculations, particularly for what were considered minor fabrication adjustments, like using 2 hanger rods instead of 1. After the walkway collapse, state boards and professional associations made it explicit. Any design change that affects the load path or capacity requires a full engineering review and recalculation. Building codes and review processes were amended to ensure that connection details, often overlooked in the past, received the same level of scrutiny as major structural elements. The collapse exposed dangerous gaps in the communication between engineers of record, fabricators, and contractors. Many states subsequently revised their laws to clarify that engineers remain responsible for the integrity of the design, even when fabrication details are delegated. And finally, the Hyatt case became a cornerstone example in engineering ethics courses across the US and internationally. It's now taught as a cautionary tale of preventable failure in many engineering courses. I remember learning about this even working through how the load calculations changed as an assignment for one of my undergraduate engineering classes. It's one of the few engineering disasters where the mechanism of failure is simple enough to be taught in an introductory class, but with profound consequences. The Hyatt Regency collapse remains one of the deadliest structural failures in US history. Gillam spent the rest of his life speaking publicly about engineering ethics. In interviews, he described the weight of knowing that his seal had authorized a design that could never hold. "The Hyatt collapse changed my life," he said years later. "It should change the way we all practice engineering." Today, at the site of the hotel, a memorial stands not far from where the walkways once hung. It bears the names of the 114 people killed on July 17, 1981. In 2015, after years of fundraising by survivors and local advocates, the Skywalk Memorial Plaza opened just outside the hotel. The Hyatt collapse is often described as an engineering failure, but that's not quite accurate. The collapse of the skywalks was a result of a failure in the social and professional systems governing the project, not a fundamental scientific error. It was the people and the system that allowed for the design to be constructed and the constant assumption that someone else had checked. The American Society of Civil Engineers commissioned its own ethics review afterwards. This review prompted the society to strengthen its Canon 1, the obligation to hold paramount the safety, health, and welfare of the public. For the first time, the Society's Code of Ethics explicitly required engineers to question design changes made by others, even within the same firm. Beyond the classroom, the event reshaped practice itself. Building codes were rewritten to demand independent structural review of all major public projects. Kansas City introduced mandatory third-party checks for connection details, the very level where Hyatt had failed. Nationally, the American Institute of Steel Construction and the American Concrete Institute updated their specifications to clarify the responsibility chain between design engineers, detailers, and fabricators. The shop drawing review process, once a formality, became a legal safeguard. Engineers were now required to either verify or explicitly reject every deviation from a sealed design. No revision, however minor, could proceed without written stamped approval, accompanied by recalculation. Within a decade, that requirement spread across the US, embedded in city codes, professional liability contracts, and accreditation standards. 4 decades later, the Hyatt collapse remains one of the most studied structural failures in history. The hotel itself was rebuilt, its lobby reopened in 1987. If you like this investigation into the engineering and ethics behind the Hyatt Walkway collapse, You might also like my recent video on Google DeepMind's work to finally solve a $1 million equation that has challenged mathematicians for centuries.